He's particularly interested in verification of proof-assistant kernels and meta theory in general. And today he's going to talk about verifying dependent type checkers.
Thanks for the introduction, and congratulations to all of you for surviving almost to the end of WITS. And to the end of the week, I'll try to make it so that you survive. Oh. All right. I'll try to make it so that you survive another hour. And so I want to talk about kind of verification aspects of different type checkers, and basically the very high level message is going to be basically the same one as the talk we just had by Ning, which is that we should be a bit more serious about verification aspects of what we're doing. I want to start with a disclaimer, which is that I've written actually exactly one type checker in my life, and this was for also rather simple type theory, like Martinov type theory was like sigma, pi, maybe one universe, something like that. Not the sort of crazy things that you see here, GHC or ROC or anything like that. So I won't be able to tell you that much about fancy type checkers. However, instead I'm going to do propaganda. And I'll be doing that propaganda because the only type checker that I ever wrote was fully verified. So this is what I know how to do. And I want to tell you a little bit about this and hopefully take some lessons that are maybe a bit more widely applicable. And so kind of my motivation is that we keep telling the world that formal verification is amazing, formal methods are really cool, they all should verify their very critical code. And then we have this whole verification ecosystem and all these fancy infrastructure that relies ultimately on these proof-assistant kernels, which are really dependent type checkers. And then we still don't have verified kernels. So I don't know about you, I'm kind of bothered by this, that like if we can't use our own tools to verify our own critical code, like what are they really that good? I'm not sure. But there's something I feel interesting happening here, which is that the code of these dependent type checkers, or more generally of dependent of like type systems implementation, the programs are not that complicated, by which I mean that they're typically in a functional programming language, reasonably pure, or at least not doing too crazy things with effects, and you don't get like crazy concurrency primitives or these sort of things. Like you don't need full-blown iris from just the latest version to verify very weird programming pattern when you do this. However, the reason why these reasonably nice programs work are complicated. So the hard bit is not really in the code of the program itself, it's in the justification for why this programs work. The one analogy I know is things like primality tests in like numerical computation and things like that, where maybe the algorithm you can describe to, I don't know, an undergrad, but the number theoretic reason why that particular algorithm works maybe requires to have a PhD in number theory to actually understand why the tests work. So I think it's the kind of similar things being at play here. That's the justification for the working of the algorithms are quite difficult. And actually, if you look at kind of the field of these things, there's kind of two worlds happening. On the one side, you have the world of what I'm going to call meta theory. So this is the world where we do things like logical relations, where we build models, and if you're kind of hardcore, you're probably going to present things in a very algebraic way, maybe even presentation-free way. That's for the category theorists. You characterize on syntax as some sort of universal property, things like that. And kind of the point is that on this side, you don't really care that much about the computational content. Maybe if you're lucky, you're going to do the proof in a constructive meta theory, but the actual content of that proof is very unclear. If you were at Mathieu's talk earlier today on algebraic universes, extracting an actual algorithm from a constructive proof by Thierry Coquin is a hard problem. So that's the meta theory side. And then the other side is the side of more what I call verification. And here we care about the actual algorithms. We even care about their efficiency. So we care about how things execute. Maybe we want to extract programs that run from our if we started from something in a dependent type system, we want to extract it to actually be able to run it. And we're going to also care about things like data structures and invariance on these data structures or throughout the algorithms. And as I said, kind of the hard problem is that these two worlds are not kind of isolated, because in order to verify all of these things, and in particular to verify all of these invariants, we're going to need a lot of these meta-theoretic properties. We're going to need to know a lot of things about our type systems to argue about the correctness of what we're doing. But still, these are still two different worlds, and ultimately we really don't care about the same sort of things on both sides. So I think it's still important to think about these things in a somewhat separate way because we have different concerns there. And there's a lot of focus on the meta-theory side. If you go look at arbitrary conference around dependent type theory, you probably see a bunch of proofs of normalizations and categorical semantics of things and whatnot. And these are things that are relatively recognized. But I think that and kind of part of the whole value of the WITS workshop is to say that actually there are also very interesting questions on the other side, what I call the verification side. So, I mean, we had the talk earlier that asking what is the abstract specification of your type system, and so often you want to kind of decouple things as much as you can, but then also try to still have some sort of a nice way to present what your implementation is doing, and it's not always that easy to do that. And also, we saw this well in the talk about lean learning this morning, that also even data structures, you also want to have the same sort of thing. We have kind of a data structure that's kind of the one that you actually want to use for implementation, maybe contain some caching information, some hashes, or some like low-level functional programming tricks. But then this is not the thing that you want to use when you do your meta theory. So there again, there's some sort of a decoupling happening. And of course, all of these implementations and these data structure, they rely on a bunch of invariants that are typically not visible in the abstract specification, but they're very important for the actual good working of what you have in the implementation. And as I said, all of this depends on meta-theoretic properties, but it's nice to be able to kind of identify what these properties exactly are and how they come into play into what you're doing in your verification or in your implementation. And so these are questions that are already worth asking on kind of, let's say, idealized type systems, the sort of things that you would see in a paper here at Popple, for instance. But these questions are especially even more interesting if you look at the things that are happening in realistic implementations. Because I don't know if you know, but actually what's happening in ROC is not quite what is described on paper. There are all sorts of very dirty details and the guard checker and the non-uniform parameters for inductive types and in the universe levels. And so there's a lot of tricky things happening there. And I mean, I'm talking about ROC because this is the thing I know best, but I'm sure you can find the same sort of dirty details in AGDA, or I think Lean is also getting fast at being as crazy as all the other players there. So yeah, Mario's nodding, so okay. So nobody has really kind of implemented the nice ideal system that they have on paper, and so this gives even more opportunity for like bugs or issues or subtle implementation problems that are not really visible on the side of the meta theory. And so I think all of these questions are important and interesting, that we should really be more serious at attacking them. And so basically this talk is going to be propaganda to say that we should really look at these questions, we should really think about verifying our implementations. And that this is an interesting question even if we don't do the meta theory. So I think it's still an important question, an important approach to take that, to say, okay, I described the abstract type system that I want to verify against. I assume a bunch of properties of this subsystem that I'm not going to show, and maybe some crazy category theorist is going to come and show them for me. That will be very nice. But at the moment, this is not what I want to do. What I want to do is I want to verify the implementation against that specification and its properties. And I think this is already an interesting question because first, it gives you a lot more confidence in what the implementation is actually doing, and also because it helps you pinpoint exactly what sort of properties you are relying on the meta theory side. This is not always that clear a question, and you'll see that a bit later in the talk. And I think surfacing these sort of actual properties that the implementation relies on is also an interesting thing to give to the people on the side of the meta theory. Say, see, these are the properties I care about. Can you please show them for me? And so basically, this talk is going to be kind of a little tour of case studies in that space of things I've done in recent years. The first half is going to be about pattern matching in meta-ROC, this formalization of ROC in ROC. So if you want to look at what's happening there, the big paper is this JCM paper from last year, just kind of telling you about the whole project. And the thing I'm going to talk about more precisely was presented by Mathieu Sozo at WITS. I think it was the first edition in 2022. So I'll be kind of talking about this thing a bit again. And the second thing I want to talk about is this question of how to verify untapped conversion checking, which is something that is used for instance, in the kernel of Rock, but has a specification which is not entirely clear. And so I had a paper at FSCD a few months ago also trying to clear up this question. I want to tell you more about this bit as well. All right. So first, with MetaRock and this curious case. So for those in the room, maybe not everyone has heard of MetaRock. So the idea is, the heart of MetaRock is this crazy dependent type theory called PQUIC, for the predicative calculus of inverse polymorphic inductive constructions. And this is a dependent type theory that's supposed to kind of model more or less what's happening in Rock. And when I say more or less, the whole point is to be as precise as possible, as close as possible to what's actually happening in the actual kernel. So we have inductive and co-inductive types and quite complicated ones. We have pattern matching and fixed points, because this is what Rock has, because it wants to kind of be as close as possible to OCaml, so that extraction can work out quite nicely. I see people nodding in the audience. That's the way I think about it. And then there's this whole fancy universe conundrum and cumulativity, which is mostly hidden to users until it is not. And then you have the worst errors ever. But that's also quite a complicated thing. And that's also part of what's happening in PQUIC. And so the goal of MetaRock is to kind of describe, formalize all of that in Rock. So have this formalized meta theory of PQUIC, try to prove as many properties as we can about it. And then we have a verified type checker. And that verified type checker relies on a normalization axioms, on one normalization axiom, a few more axioms related to the guard condition, which is kind of what powers this normalization. And there's two reasons for doing this. The first one is that we would not be able to prove that thing anyway because of like Gödel incompleteness. Normalization implies logical consistency, and so you can't prove the logical consistency of Rock inside of Rock itself, so you can't prove normalization inside of Rock. The second reason, maybe the more honest one, is that normalization is hard. Normalization for PQUIC would be very, very hard, so we haven't tried anything there. But anyway, we know we wouldn't be able to even if we tried, so like, let's not even try. But that's already kind of the spirit of like, okay, let's verify the thing and maybe assume some things on the way. It's okay, normalization is a very well-studied property. Like everybody kind of believes it, I guess. Maybe not for PQUIC, but for maybe more reasonable type theories. But that's not the thing we want to focus on. And then there's also this whole verified extraction pipeline, mostly done by Yannick Forster. So kind of the first half that goes to an intermediate language called Lambda Box, which does basically a proof erasure, because proofs are irrelevant, they're not computationally interesting, so we can erase them all and make evaluation much faster. And then there's a bunch of backends. So the original one was to OCaml or something, an intermediate representation of the OCaml compiler, actually, to avoid problems with typing. But there's also other backends to C, called Certicock. I think Bas Spitters and his group have a backend to WebAssembly. And there's also a number of other front ends that target Lambda Box. So it's kind of a small ecosystem of verified extraction compilation. And the last bit is about meta programming. So the idea is also, once you have a representation of Rock, its syntax, some of its type system, and so on inside of Rock, you can also use that to power meta programming. And for now, it's maybe a little bit underdeveloped, but we're trying to also push what's happening on this side. And for me, maybe my badge of honor with this whole work is that we found a bug in Rock, like the real Rock kernel, the very one that some of you use every day, some of you don't want to touch, but the real thing. We found a bug in that kernel using kind of our formalization efforts in MetaRock, and that's the thing I want to tell you about. So to kind of understand and kind of set the scene for what happened, you have to go back quite a while. So in the very early version of Rock, Coq at the time, there were no inductive types at all. That was kind of boring. And then inductive types were added to the system. I didn't write down which version it was, but it was quite early on. And then, but then like programming with inductive types and recursors is quite annoying. And so in 6.1, pattern matching was added into the system in the kernel by Christina Cornes. And at that time, the kind of representation that was chosen, I think, for backwards compatibility reasons. And basically what happened was that the representation of the binders in pattern matching was using lambda abstraction. So basically the branch was a lambda abstraction of all the things corresponding to the argument of the constructor. That made it easier to relate that to what was before with recursors, because this is basically how you handle things when you work code for recursors. And then fast forward a bit, in 8.4 we got universe polymorphism. It was the work of Mathieu Sozo and Nicolas Tabarot, to make things life easier to the hot people at the time working on univalent foundations and things like that. And then in 8.7 they even added something fancier, which is cumulative inductive times. So I won't get into the details just now, but the point was to make kind of inductive times a bit more compatible with this universe polymorphism. And the theory was worked out on paper by Mathieu Sozo and Amin Timani, and they had a set theoretic model telling you that everything was white. However, they only did that for eliminators, recursors. So they didn't treat pattern matching and fixed points. They only handled the somewhat simpler construction that was more reasonable to treat. So you can see maybe already the scene setting up for the issue. And then in the meantime, people liked less and less this kind of old clunky pattern matching representation. It was very strange because it was presented to users was not really the representation that the kernel saw. So there were a bunch of strange discrepancies, and a lot of work was spent into maintaining this kind of ad hoc representation so that things could be printed to users in the right way. So it was quite messy and quite complicated. And I think at some point there were various attempts at PRs by Hugo Herbelin and Pierre-Marie Pedro on making this a little bit better. But anyway, like, people were growing a bit annoyed, but nobody was really kind of ready to tackle the problem. And then in November 2020, I was probably locked down in my room and trying to learn what this whole meta-rock thing was doing. And more particularly was trying to, at that point, to prove that the type checker that we had in meta-rock was complete. So that all the things that were well typed according to the theory were actually accepted by the type checker. And this is typically the kind of hard direction in these things. And then I went to Mathieu and said, like, hey, I think there's something slightly fishy in what I'm trying to prove. And then Mathieu looked at it for 2 hours, and then he opened this issue on the GitHub of Rock, not meta-rock, but Rock, saying like, hey, actually there's something wrong in the kernel. And I think, so this is a screenshot I took at the time. I think after that they removed the inconsistency flag because it was only a completeness problem, but you couldn't really use that to prove false. But still, like by looking at things hard, we found a bug that was exactly replicated in an identical fashion on the Rock side. And so at that point, like, Mathieu had a relatively quick and dirty fix. It took him maybe a day or two to kind of tweak things to make them go reasonable again. But I think that was kind of the straw that broke the camel back, and then like that was enough motivation to finally attack this weird representation of pattern matching. And so in the next version of Coq, we had this complete redesign that people had been thinking about for a long time. And the good thing was that this was done in parallel in Rock and meta-rock, so we could kind of make sure that what we were doing was reasonable. And at that point, I managed to finish my proof of completeness, so everything was fine again. And just for fun, I want to show you exactly what was happening there. So this is issue 13,495. There's a lot of issues on the Rock GitHub. So if you've played with dependent pattern matching in Rock at some point in your life, you've maybe seen this kind of crazy syntax. So the pattern matching, so this S here is the thing you're matching. And because of dependent pattern matching, you can't just give so this is the return type, this is the type that all the branches are supposed to have and that the entire pattern matching is going to have. But because it's dependent pattern matching, that P is not quite as simple as you might expect. It actually binds a number of variables, which are this X and ints here. So these ints here are the indices of the inductive type that you're matching on. And this X is going to kind of stand for the scrutiny. It's going to be generalized in the branches and then kind of substituted by the scrutiny at the end of the pattern matching. And so from like Rock 6.1 to 8.13, the thing went more or less this way. So we would first start by inferring the type of S, and that thing should be an inductive type with a number of parameters and indices. And then you basically want to check P against a type that looks like this. So you generalize over all the indices of your inductive type, substituted with the parameters. You have this extra variable standing in for the scrutiny, so its type is and the inductive type with the same parameters but kind of generalized indices. But the problem is that the universe in which that whole thing is supposed to live is not known at that point. And then you check the branches in kind of a similar fashion, and at the end of the return P. And so what's happening there actually is that, okay, so you can't really directly literally check P against that because there's kind of a hole in your thing. So then what you're going to do is you're kind of going to do by hand what that check would have done. So you're going to infer the type of P. You check that this type is of the form, some sort of a big product type of a bunch of things, and then a universe at the end. So this L is kind of the thing that is going to fill in your question mark here. And then you check that this context that you got here is actually the one that you expect, that both of them are definitionally equal. Now, question to the audience, can you spot the issue?
Why do we still have a question mark?
Here, because now, I mean, once you're there, you know that question mark should be L, and then you can proceed. Okay. Okay. Nice. So it's good because basically nobody was able to find the issue between. It was not 6.1. I think this was introduced in 8. Whatever when 8.7 when cumulative inductive types were introduced. So between 8.7 and 8.13, nobody was able to spot the issue. The issue is actually here. You should be using super typing instead. And so, as I said, in P-Quick, you have this cumulativity, which is a limited form of subtyping, which includes universe levels. And the point is that here you really should be using that thing. Otherwise, there are certain things that will be typable with respect to the specification, but that will not be caught by this test. This is a bit the conversion test here was a bit too restrictive. And so the real thing, so the kind of the quick fix by Mathieu was to just change the Boolean here, basically, and that made things a bit better. But the real solution was, instead of having this kind of P that should have a pi type, is to instead check that P is a type in the context where you add these three variables directly. And it's kind of doing the same thing as here, but this will kind of include this super typing thing kind of implicitly in the way the type of variables is handled, and then everything will be good again. But so I think this is a typical example of the sort of things that happen in this implementation. So it's a combination of a lot of things. So it's an implementation. I don't know if it's a bug. I would call it more of a misdesign. It was really kind of intentional. At some point, Mathieu chose to use the wrong thing here. It's not like he just forgot a check or forgot a function or used the wrong one by mistake. He thought he was doing something fine, but actually did not use quite the right thing. But this thing happened on a combination of advanced features. So like really here you have all of the dirty things of P-Quick all at once. You have pattern matching, universes, complicated inductive types. So all of them at once. And even worse, this combination had never really been looked at on paper in detail. Probably if Amine and Mathieu had like sat down when writing the paper and looked at pattern matching, they would have realized that there was something going wrong here and done the right thing. But because it was not described on paper and even less formalized, nobody really looked at this thing very hard in the eye, and so the bug was able to slip. And so I think this is kind of a lesson of like the sort of things that verification can bring to the table. It forces you to look hard at gory details of your implementation. It forces you to be honest as to what is actually implemented and not some sort of idealized thing that you present on paper. And then it can catch these sort of things that otherwise easily slip through the cracks. Okay, so that was the kind of the meta-rug story. Now I'm going to switch to the other one, and in this one, so the question is a bit more blurry, but the idea was so when you have a dependent type checker, kind of the biggest complicated piece of your type checker is a conversion checker. So something that checks for definition equality. I mean, in P-Quick it's a bit more complicated. You have subtyping in there, but let's ignore that for now. And in this setting, and Stephanie explained that already quite nicely yesterday, you have on the one side this kind of nice declarative specification, which says that your conversion is an equivalence relation, reflexive, symmetric, transitive. It has all congruences, and then it contains a bunch of interesting kind of base cases. The most common ones are computation laws, so-called beta laws, so I don't know, the one from the lambda calculus, or match on the constructor and things like that. And if you're a bit wilder, but it's really important for actual usage, you also have extension intervals like eta for functions or for pairs or records in general. And also in Pickwick, we have strict propositions that also have some sort of an extensionality. And this is quite important practice for like performance reasons, but also there are certain things that you just can't show if you don't have eta, and some people really care about this. So we're going to give it to them. And I have a strong opinion on this, that this one should be typed. But like if you want to do the meta theory, especially of eta laws, it's much, much nicer if you have some kind of typing constraints on how you handle this thing. And there are certain things that just you can't really express if you don't have type constraints here. So I like this specification to be typed. But then in the implementation, there's kind of two things you can do. The kind of maybe more naive implementation is a type-directed one. So on the high level, what you do is you alternate kind of three phases. The first one is going to be doing beta reduction until you hit the weak head normal form, so something that's kind of reasonably stable. And because you have a type, you do this to the two things you're comparing and also to their type. And then you first look at the type, and if the type is kind of one that admits one of these eta laws, for instance, the function type, you're going to apply that eta law, and then recursively go back to step 1. And if it doesn't, then you go to step 3, and then you're going to try to apply kind of one step of congruence, looking at what your terms look like, and then go back again to step 1 in the subterms, and then you just do that on and on again. The maybe more complicated or crazy, or maybe not, depending who you are, is the untyped algorithm. So this one doesn't maintain any type information. So, but it's still kind of the same structure. You first do beta reduction to weak head normal forms. Now you can't look at the time to know whether you should trigger an eta law. So instead what you're going to do is you're going to be term directed. So you're going to say, oh, whenever I'm trying to compare something that's not a lambda abstraction to a lambda abstraction, I'm going to eta expand the side that's not a lambda. And this is due to Thierry Coquin for quite a while ago. And yeah, so this is kind of a way of reconstructing the type information that you're missing in some sort of term directed way. And again, if none of these things apply, then you just try to apply the right head congruence. And these are the kind of two things that we want to relate to this declarative specification. And so yes, so this one is a bit closer to the specification. It supports somewhat fancier rules. For instance, it's really annoying to do eta for the unit type on this side, because this is something that really wants to have type information. In general, I mean, this is a controversial take. Some people say that this one you can still implement in a very efficient way, but kind of naively, it's a bit slower because you need to compute things in your types, so you have more things to maintain. And also, if you're not careful, this kind of eagerly applying eta laws can also be quite performance problems. You can ask Agda people why they turn off eta for records all of the time. It's quite problematic in big developments. And then, so on the untyped side, it's generally a bit faster. It's also kind of simpler, at least on the surface, because you don't need to think about types, you just look at the terms. But then it's further away from the specification, at least if you want to take the type specification. And so maybe the simplicity is only in appearance, because like anyway, you want to relate it to something that has type information in it. And so kind of the idea of this work was to really understand what it takes to verify something like this, and especially verify it against this typed declarative specification. But then before kind of going into that, I want to kind of take a big step back and think about what exactly we want to verify for these things. So at the very, very high level, what we're trying to do is we have on the one side a property, so something from some sort of domain into propositions. So that domain typically here would be a for tuple of a context, a type, and two terms. We want to check for convertibility. And then on the other side, you have a function that goes from the same domain but now returns a Boolean, and you want to relate the two of them. And kind of the usual story we tell in textbooks goes like this. So first, on this side, it's kind of by definition that it's decidable. A Boolean is either true or false. So we get kind of for free that like P of D is always either equal to true or false. So decidability on this side is trivial. And then you show soundness. So you show that whenever the thing says yes, then indeed the property holds. And then you show completeness. So whenever the property holds, indeed the function answers true. And then you're happy. You have decidability on this side. You know the two are equivalents. You also get decidability on this side, and then use that in your type check. Except that actually things are not that easy, at least if you're looking at like conversion checkers. And the problem already happens in the step 0, which is that we said that the thing is decidable, but actually this is more reasonably. I mean, the more reasonable model here is a partial function, because a priori, knowing that the type checker always terminates is quite a hard thing to show. It's related to this normalization property I was mentioning earlier. And so in general, it's hard, like this thing is not structurally recursive at all. So already step 0 kind of fails. Step 1 is usually kind of fine. Typically, if your type checker answered yes, it has kind of constructed some sort of a trace of whatever happened. And you can look at that trace and convince you that all of the steps that applied were reasonable steps, and that they can kind of be matched on the side of the specification, and that you're fine. Completeness, again, is kind of problematic because, as I said, we want the specification to be reflexive. But if you look at what reflexivity entails on this side, it says that anything kind of related to itself, and the way the algorithm works is going to do this iterated beta reduction. And so basically, reflexivity will imply some sort of normalization or termination. And again, as I said, it's a difficult property, so maybe it's one that's not that easy to prove. So my claim is that this is not the plan we should follow. Instead, the plan should look like this. So first, we show positive soundness, and I've called it positive now because you'll see why in a second. So this one is still the same. You show that if the algorithm answered you yes, indeed the property holds. And that one, as I said, you look at the trace of the type checker, see that it has done only reasonable things. That gives you the positive soundness. But then in step 2, I think we should rather show negative soundness. So we kind of flip things around and we say, if the type checker answered no, then we can indeed conclude that the property doesn't hold. And kind of the advantage of this version is that, again, we have the entire trace of the type checker. We can see what it did and why it concluded that something was not possible. And so in particular, we have kind of no termination property. We already know that the type checker terminated just with a negative result. And so we don't have to think about termination. And if we look at this trace and think a bit harder, then we are able to conclude that the property doesn't hold. And then in step 3, you still have to show termination of your partial function. That is still hard. But in a sense, you already have 1 and 2, you're already quite happy. You know that your type checker is never going to lie to you. And maybe that's OK. I mean, you can even be lean and be crazy and implement some non-decidable thing. But at least you know if the kernel said something to you, you can trust that thing. And I think in most cases, that's the one thing you really care about. In particular, you really care about the fact that the type checker will not tell you, oh, this thing is not typable, if it actually is. That's kind of the bad thing that you can get. But if you have 1 and 2 already, you're quite happy. And so this is, in my opinion, quite a better plan. And so let's look at what we can do to obtain that thing for our typed and untyped conversion checkers. And so this is kind of the FSCD paper. I'm not going to go that much into detail. I'm just going to tell you kind of the very high level how things go. So on the left side here, you have kind of the big meta-theoretic properties that you can think of for a dependent conversion in a dependent type system. And at the top here, you have these properties of the actual implementation. And basically, there's a cross if you need to use the property on the left to prove the thing on the top. Okay. So the first thing to see is that actually positive soundness doesn't require a lot. It just needs this type constructor injectivity property. I mean, that's still not that easy to show because types in dependent type theory, they can compute in all sorts of complex ways. So showing that they're injective is not that easy. It's still a non-trivial meta-theoretic proofs, but that's basically all you need. And then if you want to have these negative soundness, both typed and untyped conversion, you need to also have, so injectivity are the important properties. You need also to have some more term-level injectivity, because typically what the conversion checker is going to do is if you're comparing, say, successor of something to successor of something else, is going to apply a congruence rule. And what you need to know is that congruence rule was kind of forced. It was a forced trust. There's no other way to conclude the successor of t is convertible to the successor of t prime. The only way to conclude that is if t and t prime are convertible, definitionally equal. And so you need all of that for all of the constructions in your language, basically, to be able to conclude negative soundness. But that's still fine. And termination really only is, it's constant with normalization, but you only need normalization for termination. So that's kind of isolated nicely in its own little corner. So kind of the plan that I had at the few slides earlier is kind of a reasonable one. And the second thing is to notice here is that even though this implementation of untyped conversion looked like it was not maintaining type information, if you want to verify it, the first thing that you're going to do is you're going to write down invariants that are going to have typing information in them. So I think calling this untyped conversion is not quite reasonable. I think it would be better to call it term-directed conversion would be a more honest name for it, if you're really trying to verify it. And just for those who want to see big symbols, this is the sort of properties you want. So this injectivity of type constructors says something like, if you know that two types are definitionally equal, convertible, they're both in weak and normal forms, then you have kind of a long list of things, but the point is that you kind of have to be on the diagonal. So either they're both nats, or they're both pi types, and then the domains and the codomains are recursively convertible, or etc. for each of the possible types in your system, or both of them are neutrals, and then they're kind of convertible somewhere lower down. I'm going to come back to these neutrals in a moment. And this is exhaustive, meaning that also any non-diagonal case is impossible. So it's not possible to have nat convertible to pi, for instance. And that's also very important. So that's the type constructor one. You have the same one as nat. So if you have two weekend normal forms of type nats, then they're both either 0, both successor, or both are neutrals. Kind of the same sort of dichotomy, trichotomy, and so on and so forth for all the other types in your language. And a normalization in this work is phrased as some sort of inductive predicate that's saying that kind of this iterated weekend normalization and inter-expansion kind of terminates. And maybe the thing to note here is that this is a rather intentional property. This is not the same sort of thing that kind of presentation invariant properties that the people on the meta theory side like to say. So I need something telling me something a bit more precise about reduction. So there's some sort of a discrepancy here that is kind of interesting to resolve maybe in the future. Okay, and now the one thing that I want to look at a bit more closely is this untyped conversion, because I kind of lied to you here. I mean, it looks like this is exactly the same cross in both cases, but actually not quite. And there's a catch there, and that catch is on these neutrals that I mentioned already. So for those that maybe might not be too familiar with the meta theory of dependent types, so neutrals, they appear once you start to think about open terms. So in kind of traditional programming languages, typically you're concerned with evaluation of kind of closed expressions, and ideally at first order types. So typically the sort of things that you're going to evaluate is like a closed Boolean, a closed natural number, these sort of things that you're going, I don't know, to print to a user or something like that. But you don't care that much about what's inside a function. If you ask OCaml, it's just going to say closure, and that's it. And so you don't really look inside these things. But for dependent types, if you want to do conversion, you really have to look inside these things. You really have to go under binders. And once you go under binders, you are looking at open terms, things that contain variables, and there things can go a bit more complicated. What's happening there is that you have these kind of extra normal forms, things that kind of cannot really compute further because they're stuck on a variable. So kind of the ultimate neutral is a variable that cannot happen in a closed case, but it can happen in the open case, or more generally, you can have kind of a bunch of eliminations kind of stuck on knowing what this variable looks like. So the typical neutral would be something like this. So you have this variable here in your context that you then apply to an argument, and do a projection of that, and do another recursion on that, and so on and so forth, and just kind of keep piling up eliminations that are waiting to know what x is going to be to compute further. And if you want to do conversion, you really have to think about these neutrals. And so the kind of two question is, how does one compare these things? And where does this comparison happen in your algorithm? And this is the place where the two implementations, the typed and the untyped one, differ quite widely. Okay, so I said this one is type directed and this one is term directed. And so what happens if you're looking, so this is kind of a very dumb problem. So you have one variable in your context of a function type, and you're comparing it to itself, okay? And I'm going to highlight in pink here the things that kind of drives the algorithm, the thing that's used to decide what's going to be the next step. So the time-directed algorithm, what it does is it looks at this thing. It says, oh, so already everything here is in weak-head normal form, so you don't need to perform this beta reduction, otherwise it would be necessary. But here you're already in weak-head normal form, so you look at things and you look at the type first, and you see, oh, it's a function type. I'm going to apply eta expansion. Okay, so now you introduce a new variable in your context, give it as an argument to your things. And again, here I'm skipping. In principle, you would have to do another step of beta reduction. Here, everything is in weak-head normal form again, so you don't need to do that. And then you look at the type again, and the type now is nat, and nat doesn't have any eta row. So you're going to look at the terms. And these terms now, they're both applications stuck on the variable, so they're neutrals. And this is the place where you kind of change mode, in a sense, and you go into this new relation, which is, so this squiggle here is this neutral comparison kind of subroutine in your conversion checker. So now you change mode, and you look at your neutrals, and you see they're both applications. You're going to apply the congruence rule of application, and you're going to compare x to itself again. And now this is a base case. This is a variable that's in your context. It's the same variable on both sides, so you're going to accept. And then on the right-hand side, you're going to compare the arguments, and you're going to compare the arguments in general for conversion again. And here, it's a variable again, so you're going to do the kind of the same thing as here. I'm omitting that part. And then you can see a bunch of things. You can see already this kind of inefficiency I was mentioning at the beginning. Like here you did an eta expansor that was not really helping in checking that these things were convertible, because I mean you had a variable here, so on both sides it's not really necessary. So you see the extra work, and you also see this kind of this switch here happening only at kind of the base types, at least the types without an eta law. And the turn-directed conversion here, well, this doesn't have access to anything, no type information, no nothing. It sees a variable against a variable. It's a neutral, so it kind of still does the switch to the neutral mode, but then it concludes immediately because now it's a variable already. And so you see kind of the difference in the amount of work. And if here, instead of nat to nat, you had a big type that computes, and that takes quite a while to compute, it would be even more costly. But still, the question is, like, why does this thing work, or why do these two things work? But especially this one that kind of does this change straight away, even though actually this thing was at a function type, and so maybe an eta law could have helped in making the things convertible. So kind of implicitly in this algorithm, the kind of thing that we're using is this kind of injectivity property of neutrals. So kind of, again, in kind of the same sort of recipe as the one I showed earlier, something that says like, oh, if I have two neutrals that are convertible, then they're either both the same variable, or they're both applications, and the functions are both definitionally equal, and the two arguments are both definitionally equal, or etc. with, again, like one rule for each of the eliminator in your language. However, this does not always hold. So as I said, I mentioned the unit type already. This is our worst enemy. If you are in a context with two variables of type nat to unit times unit, actually the two variables are going to be convertible. And the reason is that basically you can kind of apply a bunch of eta expansion. So first, the eta expansion for records is going to tell you that if the first projection of x is equal to the first projection of y, and the second projection are also equal, then the two things are going to be equal. Now the second projection, they both have type unit, so they're always convertible. That's the eta law for unit, so that you don't have to think about this. And then the first projection, they're of type nat to unit, and then you can again apply the eta law for function. You end up with comparing again things at the unit type, and they're going to be convertible. So kind of here, in a sense, we're kind of lucky that the type here to the right was nat, but if it had been unit, then this thing would have been kind of a bit too optimistic, and maybe you would have needed to do this sort of thing here to end up concluding correctly. And so in general, the lesson is that this neutral comparison is complete only at certain types. And so if you try to prove negative soundness and you're not careful, then you'll end up into trouble. And actually, the very interesting thing to see here is that the three main implementations of dependent type theory make very different choices here. So Agda chooses the time-directed algorithm. So it, in principle, does all of the like kind of useless work I showed at the beginning. And if I understand correctly, there's some sort of short path for functions to not apply eta laws for functions too eagerly to preserve reasonable performances. But the high-level idea is still this one. Lean has a term-directed thing, and it has unit. So it has this problem that like sometimes you have to be a bit careful about unit types. And so basically there's a check in the kernel to detect unit-like types. So things like this type here, that although they're not literally the unit type, they still kind of behave like the unit. Actually, what's happening at that type is that any two inhabitants of this type are always convertible. And so when kind of neutral comparison fails in lean, you have kind of a separate check that checks that indeed that maybe the type at which we're performing this comparison actually is a unit-like, and in that case you say yes. And if I'm not mistaken, that check was incomplete, is still incomplete?
Yeah, it's not complete.
It's not complete, okay. So conversion in lean is incomplete, as you all know. So this is one of the many sources of incompleteness there. And in ROC, we make kind of a different choice. So we still have this term-directed algorithm, but essentially we forbid unique-like types. So if maybe you've seen this weird restriction about records in rock, that they need to have at least one field, and actually they need to have at least one relevant field. So they cannot have fields that are all of type S-prop, for instance. And this is the reason, because basically unit is a record without any fields. And if you have like all of your fields are then sense unit-like, then the record is going to be unit-like again. And so this is the real kind of high-level source of this restriction, is that basically by forbidding these unit-like types, by having just this one restriction, forbid anything that looks like unit in our language, and then this kind of will for the whole system forbid any unit-like type, and so we'll actually get that neutral comparison is always complete, except for 6 propositions that have a kind of a special thing where you track some relevance information, but that part is a bit more tricky. I'm not going to talk about this here, but you can ask Gaëtan in the first row about this. He knows all about this complications. But anyway, kind of by doing this attempt at verification and trying to really look at what the algorithm are doing and trying to verify them, we really have first understood that there's something subtle happening, and also have, at least for me, this is a very satisfying thing, because now I understand really what are the trade-offs that are happening in these kernels. They don't do the same, they don't take the same decisions, but they take these decisions in a, they make reasonable trade-offs, but now these trade-offs are rather easy to explain, and then you can choose which one you want in your own implementation of dependent type theory. But at least now it's rather clear. Okay, so time is running out, so it's time to wrap up. So I think that, maybe you're not the people to convince of this, that verification is useful. I hope I've given you yet another justification of why verification is nice. Of course, it helps in finding bug, but it's a bit more than that. It helps you, it really forces you to look at the dark corners of your implementation and to be honest about them, and maybe to even document them to your users. And it's also a good way to kind of uncover and understand the assumptions that you are making in your implementation. Maybe you're not really realizing it when you're doing the implementation that you have one of these assumptions, but now by doing this verification effort, you kind of surfacing these assumptions, and you understand a bit better what the sort of trade-offs are. I didn't mention it, but it's also a great way to write documentation. I think the meta-rock paper I mentioned at the beginning is kind of the best documentation there is on the type system of rock, because, well, we had to write it properly, fully, in all detail, and then we tried to explain it in a reasonable way to readers. I hope it was reasonable. If it's not, well, you can complain to me. It's also a great way to reduce folklore, because all of these invariants and subtleties of the kernel, typically you learn about them in the rock call, or I don't know how it is for Agda or for Lean, but it's really kind of transmitted kind of person to person. There's not a lot of kind of outside communication about this. I think WITS is a great place to make more of this folklore visible and surface it. But I think this verification can also be a good way of understanding really what are the trade-offs, documenting the invariants that your algorithm depends on, so that it's a bit harder when you add something to your kernel, change something in your kernel. It helps you realize that what you're doing is maybe a bit funky. And then there's maybe more than that. I think for me, at the moment, the one big drawback, as usual, is that the cost is still very high. Metarock is I don't know how many people a year were spent into this, but probably more than a dozen. And the other project I mentioned, even though it's still kind of a toy, dependent type theory, also multiple person year. So in general, there's still quite a high cost to these efforts, and I hope we can make progress there. But yeah, for now, sadly, we still have to toil quite hard to do this. But yeah, hopefully it will get better. And now looking forward, already just this week, there were a lot of cool things happening in kind of the space presented at this conference. So I've kind of tried to summarize some of them. I'm probably forgotten about some others. I'm sorry for the people in the room that contributed these. On the kind of the big proof assistants, kind of each of them now has their own homegrown verification parts. So in Agda, there's Agda core, which is at the moment trying to verify the Agda style pattern matching, which relies on unification, also the termination checker. There was a poster about this in the poster session a few days ago, and as far as I understand, it's still quite actively worked on. On Lean for Lean, the thing that I find really interesting, that's really trying to mimic what's happening in the kernel code with like the caching and all the C++ hackery just mirrored into Lean, and also having some sort of program logic to deal with it. And this is, I mean, what happens when you try to verify proper programs. You invent a new program logic to deal with them. So apparently Lean 4 also does that. On Metarock, the thing that I'm really excited about is that the latest additions to the Rock kernel, things like algebraic universes, nested inductive types, they're kind of tested at the same time in Rock and Metarock. So the thing is kind of mature enough that we can really work on it to understand the implementation that we want to do. And for me, this is a great progress, and I hope it really helps us better understand what's happening into these systems, and hopefully maybe help us move actually faster by helping us stay reasonable, but also giving us good confidence that the thing we're doing is actually a sensible thing to do. I mentioned this Lambda box, which is growing into a whole ecosystem of all sorts of verified compilation, extraction, erasure, and whatnot, which is, I think, quite a nice thing too, especially because at the end of the day, if you want to extract your type checker, this extraction mechanism is also part of your trusted code base, so you better have a good story there. And then there's much more, maybe more on the side of the meta theory. So the log-graded is a project we have, the second one I mentioned. There was also this week this log-graded elementity, which is now apparently called graded type theory, was also mentioned, the work of people in Sweden. There's this MACTT formalization coming from McGill, Brigitte Pienka and her group. There was a paper by Stephanie and Yiyun also at this POPL, yet another project in this direction. So there's a lot of things happening, lots of fun things. Oops, I have lost my, yes. And so maybe the biggest thing here is that we hope we can lower this cost. We're building a lot of libraries for now. They're kind of scattered, but hopefully you can build more reusable things and also general insights on what's happening there. I have lots of hopes for automation. For now, automation in these things is mostly not very existent, but it's a very useful thing. We're using this autosys library for substitutions. The Matisse presented Sulfur today, which is also going in that direction. I think we can do much more. And hopefully, I mean, once this kind of big flagship projects become a bit more stable and well understood, hopefully they will be also easier to fork. If you want to kind of work on your own extension to the Rock kernel, maybe you can just fork Metarock and then go on with your own life. And maybe the one thing that's kind of still a big question to me is how we bridge this gap between the more meta-theory-oriented formalizations. There's also a lot of things happening in that space, and for now the tools and even the definitions are not quite the same, especially around this question of like kind of representation independence and characterizing things with universal properties. There's also kind of a gap here that we'll need to look at, but quite an interesting one, I believe. And so yes, so we can and we should separate these two aspects, meta theory and the verification, but still we should also find these right interfaces, and then maybe one day we'll have this entire formalization all the way from this fancy synthetic categorical methods for normalization and meta theory all the way to Metarock, and I hope beyond maybe verifying proper hardcore efficient implementations of, I don't know, universe levels, things with maybe down to the concurrency and whatnot. A lot is happening in that space. There's a lot of things moving, so stay tuned, or even better, come join us. It's quite fun, quite scary, but quite fun, really. And that's it for me. Thank you.
Thanks for your talk. Very nice work. So I have maybe a stupid question. So if we mechanize this kernel in the proof system itself, can we reduce the TCP, the trusted code base? Or if we can, how much we can reduce?
So that's the kind of the universal question. Like, what's the point of looking at the logic inside of itself? So there's two things. The first one is that actually verification, you're not really thinking about like consistency or whatever. What you're doing is you're reducing the crazy implementation to a well-specified logic. I think that part is definitely reducing the trusted code base, because you're reducing that code base to a logic. And then, I mean, at the end of the day, maybe you can be very unfortunate and do like poor old Martin Luft did in the 70s and prove the consistency of the system in basically itself, but it's inconsistent, so you're sad. There's a lot of structure to these things. The field is very mature, I feel, and I would be very, very surprised if we managed to have an inconsistency that is able to reproduce exactly itself. For me, this is not something I believe in. but then at the end of the day, there will still be a gap of trust. At some point, you will have to trust something, but I think this is still very helpful in making more reasonable assumptions and getting us towards more trust. Like I trust the parts of rock that have been formalized in MetaRock, I trust them much more now than before they were verified. And I really hope we can look at the guard checker, for instance, and I'm sure we're going to uncover terrible skeletons there. But I think once we've really looked at it through the lens of MetaRock, I will trust it much more than I do now. It's not going to be perfect, but it's going to be good.
Yeah, of course. I also believe that with the help of this verification process, we can boost our confidence very largely.
Yeah.
Okay, thanks.
I don't know. I just want to comment that in principle, so this kind of Gödel limitation is like very nicely, you can isolate it to just having one or a few more universes.
Yeah.
So I don't know. Do you have any plans to add like one more universe just for MetaRock so that you don't need the axiom?
So it's a bit tricky. So we did something like that in the logrel paper. Basically, we verify Martinov type theory with one universe, and we kind of think we used 4 or 5 in rock. It's a bit difficult to measure, but like a handful of them. For now, anyway, the sort of object theory for which we're really able to prove consistency is still very different from the meta theory anyway. Like, I mean, you have cumulative universes, all sorts of complicated inductive types and so on. So there's still quite a wide gap, but I hope that, at the end of the day, we might be able to kind of reduce that gap to maybe just universe discrepancies. I think for now, we're not there, like we're not at the point where we could just add this one really weird universe just to kind of build the consistency of the thing in itself. But maybe one day we'll get to that, and that would be a very, very satisfying moment for me.
I have a question for you. That argument works in impredicative universe hierarchy. But for the predicative part of the theory, how do you do that?
No, I think like Pickwick with n universes should be like logically weaker than Pickwick with n+1, and hopefully you could show the normalization of Pickwick with n universes and Pickwick with n+1 universes. I think you'd probably, yeah.
Okay.
I'm not sure there is any proof of normalization of Pickwick with n universes or anything approaching. I mean, there were proofs of like impredicative theories at some point, but as far as I understand, even like, I mean, for me, it's not entirely clear what the status is of normalization proofs there in any case. So I think we'd like have to go for something new, but
that was like Lloyd counted once.
Yeah.
It was like 3 or 4 or something.
Yeah, so I think we're using 5 maybe, but like there's some duplication at some point, so probably you could reduce that to a few ones, and even if it's 5, it's okay. But I think it was only for predicative systems. So now for impredicative systems, we don't really have a good story, especially if it's the impredicative part computes like in rock, and there is really wild territory, and I don't know of any good modern proof of that.
Because if you do a model using logical relations in the language itself, I mean, it's clear how in the predicative hierarchy you can use one extra universe to model the universe, and you are fine. But in the impredicative part, I mean, you are exactly in Martinov territory.
Yeah, I know, and this is why we don't have any normalization proofs from an impredicative theory formalized. Like, it's a hard problem, and I don't think anybody really has a good clue there. I mean, there are things from the 90s or early 2000s, but for me they're a bit blurry.
Have you thought about like reducing the strength in a sort of different way? So like rather than having a limited number of universes, you could be using less features, for instance. Like in MetaRock, like I assume you're not using like literally every feature of inductive.
You'd be surprised. I mean, we have universe polymorphic cumulative nested inductive types, so we're using quite a lot of the features. But you're right, that's also the other direction. And I think actually we should not be attacking any consistency and normalization proofs for Pickwick itself. I think we should have some sort of verified translation passes to my core languages, and then maybe attempt some sort of normalization proof for something with like kind of a well-delimited and indeed relatively simple theory. Doing these sort of proofs while preserving normalization is a bit tricky, I believe, but I think that should be possible.
Questions? So during the development of MetaRock, you found more bugs? Or?
Yes. Yeah. So I think, so sadly we didn't find any consistency bug. It would have been really the victory. But also because we're not improving anything that looks like consistency. So maybe if we were, we could have. But yes, we did. And I think even for the parts where we did not find any problem at the end of the day, I think we feel a bit more confident of our understanding of what's happening there. And for instance, the work, I think it's a good example, is the work of Thomas Lamiot on nested inductive types. Like he's really looking hard at these things and formalizing these things in MetaRock, and like his version of nested inductive types is, in my view, much more reasonable than the one that we had before. There were like things that were accepted that shouldn't have, things that were not accepted that probably should have. Like the story was quite complicated there. So I think basically whenever we look at one of these features, even, I mean, often we find bugs, or sometimes we find bugs, but even when we don't, we really clarify the story there.
And after MetaRock, there was any bug found by somebody else?
So I think there were, but all of them were found in parts that were not verified in MetaRock. So for now, the main two sources of bug, I think, are the module system and the guard condition, which are two things that are not at the moment part of MetaRock. And I mean, it's kind of a chicken and egg problem. Part of the reason why they're not in MetaRock is that we don't really understand what they're doing. And the fact that we don't understand what they're doing kind of shows up in the fact that this is where we find bugs. So yeah, so if you ask Pierre-Marie Pedro, he's a bit cautious about this, saying basically that we're looking only at the parts that we already understand, which are not the parts where the bugs are. So maybe there's a lesson here. But yeah, okay, excellent. So I think that's one of the limitations of these things, that it's easier to look at the things that we already understand. But I think still that this is helping in putting the whole thing on a better footing. And then maybe at some point we'll also be able to get rid of the dark features that are not that used, that are hard to account for. And maybe there's a trade-off there, and then maybe the trade-off will be, okay, we'll just deprecate them, and that will be it.
What's the status of the like VM compute or the other fancy reduction strategies?
That's a very good question. For now, the version we have verified in MetaRock is a semi-naive. Like, it's still an abstract machine that does something relatively smart. I think it's close to what the normal kernel is doing, which is good, not that good. The good thing is, using extraction, you can get something that's close to Lean's decidability, where you take your closed term of type bool, extract it, run the extracted code. If it's true, then you know that the original thing was true. But the point is that here we really have a theorem that says, like, if the OCaml code says true, then indeed the thing you started with is true. And so you can use that to have a kind of an alternate evaluation, like fast, efficient evaluation that's good. And that part, I think now Mathieu exposes it in Rock. So I think now there's an equivalent of VM compute that's like a MetaRock compute or something like that, that you can use. And I find this quite cool. And I don't know what the story will be for these other things, whether we're going to maybe move towards more this MetaRock verified extraction, or whether we're going to try to verify some of that at some point. I mean, there was the work of Nathanaël Courant and Xavier Leroy also this week around these parts. So maybe some of that will end up being in MetaRock or in Rock in somewhere or another. I'm not exactly sure what things will happen there.
Thank you very much for the nice talk.